All right, let's go ahead and get started. This is the help session for project 3, which is the memory allocator. So just as general, we're going to go over memory management overall and see how to get started on the project, project structure, and then some debugging stuff, and then the actual logistics and grading of the project itself. So as a overall in C, so memory management can take place at different levels. So you have operating systems, which have to manage the memory of the entire machine. And then there's some special programs that actually manage their own caches, but that's not really what we're going to be looking at in this project. So all of what we're going to do in P3 is place the process address spaces in the heap. So address space of a process can vary between different systems, but traditionally it's all going to be right above here, and it's going to be above the part where the actual program code is. So it's all going to be in the heap. So the heap here is a continuous chunk of memory that's given by the OS to the process. So the process can access these addresses starting at the base here, and it grows upward to this point that's called the program break. And this point symbolizes the end of the heap. So if you access anything in here, the unallocated memory, you get a segfault. And if you access anything that's here in the heap, you're going to hit an object that's been previously allocated by some malloc or realloc call. So this is actually how memory corruption occurs. So if you follow a pointer that points to an address somewhere here in the heap, and it's already been assigned to some object, and you're trying to assign it to some other object, what happens is you're clobbering this new struct over the previous object, so the memory there will get corrupted. So what we're doing is creating an allocator that sort of acts as a middleman. It asks for memory from the operating system, and it gets it. So if the allocator says the heap isn't big enough, we need more space, it'll ask the OS to move this program break up so that we can get more space here. And then it will send that pointer address back to the user who requested that space. So this happens for like malloc and realloc calls. So essentially what the allocator is doing is getting a bunch of memory from here and portioning it out so that it can hand it back to the client as it makes those calls. When the user calls free, the dynamic memory allocator needs to like make a note of the block so that it's freed. It can't actually send this space back to the heap, because if you have a block that's allocated right here, if you sent this back to the heap, all of this data that's up here would also have to get sent back to the heap, because the heap has to be one contiguous block of memory. So what your allocator should do if you have a free block that's, let's say, somewhere in the middle of the heap here, it just has a sort of graveyard flag that marks this block in the heap as not in use. So then later on, when you're trying to find another space to malloc or realloc, you can kind of overwrite the data that's in that heap since it's not in use anymore. Let me just clear that. So yeah, that's what we just went over, just general heap stuff. So the heap is a contiguous region in the memory, right? So like I said, the only way to expand the heap is by pushing up that heap boundary that we just saw. So in order to do that, we have a function called sbreak or setBreak. So the user can make a call to setBreak saying that, give me this much more memory. You're going to pass in a size to that function, and it'll push up the heap boundary that many bytes. So these are the calls that your memory allocator should be making, so it can get memory from the operating system, and it'll then pass on that address pointer to the user. In terms of using it for this project specifically, you're not going to explicitly use sbreak or the break functions. You're given a file called memlib.c, and that has a bunch of helper functions that actually utilize sbreak and break. So you're not making the direct calls to sbreak, you use the helper functions, and I'll talk about those in a little bit. The general goal of this project is to create a fairly simple memory allocator. It's nothing too fancy. It's just doing what you expect of Malloc realloc free. There's a lot of Malloc implementations that are already out there. The link here is to Google's tcmalloc, which is a little more complex, but you can take a look at that and kind of get a general idea of what it's supposed to do. So when you're actually writing this memory allocator, an important thing to consider is the time versus space trade-off. So an allocator could be really, really fast, but utilize a lot of space. Like, for example, if every time somebody made a malloc or realloc call, you could just extend the heap by that much instead of trying to search for a free block. And it would be really fast because it would always know that the memory address that it's going to return is at the very end of the heap. But because you're making these extend the heap calls every single time, you're going to utilize a bunch of space, which is not very efficient. The other alternative would be using a small amount of space, and the program is going to be relatively slower because it's going to search for a free block every time, and it'd have to go through the entire heap somehow to find a free block. So the goal here is to kind of find a balance between time and space. Like, when is it worth it to kind of look through the heap for a free block and find that space? And when is it worth it to just expand the heap at the end? Getting started, as usual, fork the repo, set to private. You will be graded on Git usage again, so make sure you're doing that. These 4 functions are what you will be actually writing in your code. There's an mm.h header file which has these, so should include that in your mm.c file. Technically, you can also just call the functions malloc, free, and realloc, but we're basing this off of what's in the textbook, which I should link at the end somewhere. But essentially, you would be able to replace mmmalloc with malloc, and it should do the exact same thing. So I'm sure most of you know what malloc, free, and realloc are, but I'm just gonna go over it real quick. So malloc, given a size, it's going to return a block that's large enough to hold that given number of bytes. Free is going to mark that heap back as not in use, so it marks that for later on when you want to malloc something that's going to fit in that space. And realloc is going to be a little trickier because you do have to allocate a block of that much space, but you also have to make sure you are copying the data that's at that initial pointer into that new block. And one of the edge cases is if the new size is smaller than the size of the pointer, you have to make sure that you are truncating that data there. So yeah, this is all going to take place in one file, mm.c. You can write helper functions and everything, but you can't have any other files other than this one. Dr. Bach has an implementation of a memory allocator, an implicit version, whereas you're going to be writing an explicit version, which I'll go over in a minute. So some of the functions that you're provided, I was talking about earlier in memlib.c. Mem sbreak, it increments the the heap by that many bytes. So it's similar to making a call to sbreak, which is what that helper function actually does. It just has a little bit of error checking. You still need to do that, but it has some error checking in place for you. Mem sbreak will extend the heap by however many bytes you give. Mem heap low returns the very beginning of the heap. So if you ever need access to that, and mem heap high will return the very end of the heap, and that's inclusive. So whatever is returned by mem heap high is still part of the heap. It's just the last byte in the heap, last byte address. Yeah, more helper functions. So I'm going to go over a Dr. Box implementation of the memory allocator. The difference between what Dr. Bach is doing and what you are doing is an implicit list versus an explicit free list. So what an implicit list is essentially, it marks all of the blocks. His implementation stores all of the blocks in a single array. So you have this first block here, and this entire thing is the payload, and it has a header like struct in it, which points to the next object. But the next object can either be free or in use. So essentially, it's an array of all the possible, all the blocks that have been allocated at one point with a flag that says if they're in use or not in use. So the problem with the implicit implementation is it's a lot slower, because every time you want to find a free block, you have to go through the entire array to be able to find one free block. Like you have to start at the beginning and search through the blocks that are also in use, which is unnecessary. I'm gonna actually share the code. So this is Dr. Bach's implementation. You can see we have a few structs that we're using. So what happens here is you have a header block, which is this boundary tag. So the boundary tag has, boundary tag has 32 bits in it. So the first bit is just either 0 or 1, and that marks it as in use or not in use. And this int of size 31 is going to store the actual size of the payload that's going to be in this block here. So the boundary tag is where you're going to store the data for that payload, and the payload will store the address for the payload itself, which I'll go about. So essentially what this is going to look like is you have a header, and then you have the payload itself, and then you have a footer. So both the header and footer are going to be boundary tag objects, but the header is going to actually be stored in the block itself, so that when you're storing these in the free list later on, you can go to the header and then kind of find the end of the payload using the size that's stored in the boundary tag. So your heap should look something like this, and so on. A neat little trick is this char payload 0. What it's being used for is essentially to store the address of the payload itself, because in the heap you're gonna basically ask for some data and then cast it to this block, so that you know you're going to have a header in it somewhere, and then you're going to have this payload, which is a char of char array of size 0. So essentially it's taking up no space at all, but it still is going to have an address to it. So when you pass the address back to the user, they have that entire block of space to do whatever they want with. There's a lot of helper functions that are provided in his implementation that you should definitely be using in your code too, because it's all pre-done. You might have to modify it because, again, we're doing explicit lists versus implicit, but they're pretty helpful. As you can see, there's a lot of pointer arithmetic that goes on. So an important thing to note is, why is it a char instead of Benjamin just asked, why is it a char instead of just a void star? You could do a void star. That's actually, I was going to talk about that in a second, but that's just Dr. Bach's implementation, and yeah, that's it. It's just it's a preference, I guess. What does 12 mod 16 mean on line 53? I'm gonna get into that. That's about block alignment. I'll talk about that in a few slides. But what I was saying is you have these casts to void star, and essentially what that does is it makes it of size 1. So when you add W size or subtract W size, it's incrementing by 1 rather than by the size of whatever the size of a block object, since that's what BLK is here. Yeah, so your implementation is going to be different, but you can keep the general kind of structure of the code. So if you look in up here, and this is the Malloc function, the first thing he does is attempt to find a fit inside of the list. So this means you're iterating through all your free blocks and trying to see if this new size will fit inside of any of the free blocks. And if it does, then you place it. Otherwise, you actually have to extend the heap. So here, you can see he's using the mem sbreak function to extend the heap by however many size, whatever size is provided, and then you actually allocate the block into there. Coalesce is another good function, but that's more of a performance thing, but I'll go into that later too. Let's go back to the slides. Okay, so yeah, alignment, which is, somebody just brought that up. What the grader is going to be checking for is that every time you return a payload, its memory address is a multiple of 16. So if you have a payload here and you have this address here, basically it should be 0 mod 16. The problem that arises with this is you have a header, which is 32 bits, so that's 4 bytes. So that has to be at 12 mod 16 then. And then you're going to have a footer here as well. So header, footer. So what happens is, what if you have a payload size of like 31? Your footer is going to be 4 bytes too. So you know that here, this needs to be 8 mod 16, so that when you go and have the next header, it's also at 12 here, and then 0 mod 16 here for the next payload. So you have to figure out a way to make sure that you're padding the payloads so that they align exactly how you need them to. Since you are going to have explicit for your lists rather than like an array implementation, what you need to consider is that if you're allocating in a block that was like previously freed, you need to make sure that size is still aligned. And that kind of goes into fragmentation, which I'm going to show here. Okay, so fragmentation occurs when, let me just draw it out really quick. Ooh. Okay, so let's say we have these two payloads that have been allocated on the heap, and then the user makes a free call to this one. So this is now free. And then let's say this is of size 64, just as an example. So then this block is free, but the user then makes another call to Malloc, let's say 31. So you iterate through your free list and you find that this first block here is free. So, and it is big enough to handle this size 31. What you would need to do is then assign this block to fit 32 bytes, because even though we've asked for 31, it still needs to be aligned so that it all matches up. And you can then separate the block. So then here you add a new header and then add this part to the free list. This part here goes back into the free list because it's still a free space that's not being used by the block that we just allocated. Coalescing is a little different. Basically, if let's say if we freed this block here after we allocated this, so this isn't free anymore. But this is free. We have two blocks next to each other that are free. So in theory, together they could fit one bigger Malloc. I guess they could account for a bigger Malloc call. So what coalescing does is it goes through the free list, sees if any of the two free blocks are adjacent, and if they are, you just kind of combine them together. So this, oh. So that just becomes one huge, this becomes one big free block with one header here and one footer here. Does anybody have any questions so far? When I post the slides, I'll post better images with it, so. Okay, keep going. So yeah, that was overall memory stuff. I'm going to go over project structure and kind of suggestions into how to actually implement this. Most of this I feel like I already went over. So for defining a suitable C structure, because this is an explicit free list implementation, what you need to do is have all the free blocks inside of a list. And it's recommended that you use a doubly linked list, which is the list.c implementation that you're provided and you should have used before in the other projects. The good thing about the provided list.c implementation is that it's an intrinsic list, meaning that when you assign the free space to like a struct that has a list element in it, it's going to interpret any of the empty space in it as a list element, so you don't need to do anything more to create that free block into something that can be added to a list. And that also allows you to use all the list functions like list remove and like list pop back or whatever you need to do on the list of free blocks. So a requirement for this project is to use assert statements. The reason for this is because this project is a little harder to debug just because everything kind of takes place on a heap. So what the assert statements allow you to do is when you're writing these helper functions, you test if they're actually working. So like if you want find fit to return a certain block, you can assert that it's returning a block that's of a certain size, or when you're testing for specific implementations, you can even test if it's returning a very specific block. You need to write 5 assert statements. If I recall, my implementation had about 20 assert statements, so it does become more useful than an actual requirement. Suggestions, yeah, use void star pointer arithmetic as I showed earlier, because it makes sure that when you're adding, you're only adding by 1, so it gives you a little more flexibility there. In terms of doing your implementation in stages, what that means is the first thing you should do is not think about any performance or utility scores. Just make sure that your malloc and your realloc and your free functions actually do work. And again, use Dr. Bach's implementation as kind of a basis for this, because he's written a lot of it already, and that's going to help you a lot instead of trying to do it from scratch entirely. Start early, that means soon, even though it's not a huge project, meaning it's not a lot of code. It is a lot of complex code. And trying to get your performance score up is going to take a lot of time. So in terms of performance, there's a lot of different ways you can add performance. So there's the base explicit list, which you need to use for a free list, but we have things called segregated lists and red-black trees that you can also use to store like your free blocks in. I'm not going to go into the red-black tree too much because that's a little more of a complex addition, but I will talk about the segregated free list. So essentially what a segregated free list is it's a bunch of different free lists. So you have, let's say, 3 free lists. So the first free list is going to store all of the free blocks that are under size 32. Next one, 64, and let's just make this one 128. So then when when the user makes a call to like malloc some block that's, let's say, size 40, then you first look through, well, you first say, okay, I can't look through this list because these blocks are too small for me, but I can start looking through this list. So it's going to iterate through this list and try to find a block that could fit a block of size 40. And if it doesn't find anything here, then it would move on to the list that stores blocks of, I guess, up to 128 from there. So there's a lot of different ways to implement this, but that's more of a personal choice. It's not a hard requirement. Yeah. check heap. So this is a function that you're not required to write, but it's used basically as kind of a checker to base, what it should do is go through your heap and print out the contents of whatever structs you have there. So then when you're testing your code on some of the trace files, you can call that function and it'll print out the status of the heap. So when you're debugging, you have a function that kind of shows what the heap actually is. And GDB has some functions to do that too, but that's for debugging. Allocation patterns, basically when you're testing stuff, I'm just going to show this trace file actually. So if you look at the trace file, which is traces, let's look at one of the short ones. So this is saying how much space you have on the heap, and then these two numbers are 6 is the number of objects. So you can see the first call to A, which is going to be a call to the malloc function. So you're saying I'm allocating object 0 with size 2040. And then you're allocating size object 1 with size 2040 as well. And then the next call is to free, and you're freeing object 1 here. So essentially malloc 2040 and so on. 6 is the number of objects in it, 12 is the number of calls that are made. So you can write your own trace files to help test for edge cases, which is actually really helpful. And like testing any of your performance implementations. So if you ran the driver, I'm gonna run this on Dr. Bach's implementation actually, but essentially what you get is a few scores. So utilization is space utilization. So if you're utilizing a lot of space, it's going to give you a lower score. So you can see for these realloc trace files, the score is a bit lower because it's possible that when you're reallocating space, you have internal fragmentation, which causes like smaller blocks that you can't use for anything because they're too small for any of the alloc calls. And then you have KOPS, which is the number of requests that were made per second. So you can see for the implicit implementation, there's no throughput, which is the number of operations per second, because again, you have to go through the entire array to find free blocks. In terms of scoring, you're going to be graded on both, which I think that's in the later slide. So let's go back to that. Yeah, these are just the tools. You can go over that in your own time, really. Project logistics. Make sure you submit code that compiles, just the general stuff. There is extra credit for this project. If you look at mmts.c, it's a trivial implementation of multi-threading that uses a single lock in, it's basically the malloc functions, but it uses locks for multi-threading. When you implement the extra credit, it needs to be something a little more deeper than that, but that's something separate. Grade breakdown, 40 points for correctness. That essentially means all of the tests run without failing. And the tests are going to be run like, I think 3 to 5 times each. So if it fails on any of them, then you don't get points for that. And 40 points for single threaded performance. So that's space utilization and throughput. And that's a score that's given by the driver, and 20 points for documentation / Git usage, which includes the 5 assert statements. Just showed you the test driver. So the performance score is based on both the space utilized and the throughput. And Okay, I guess I forgot to include that, but it's mapped to 90 points. So essentially the throughput score you can get from 45 to 90 is going to be mapped to the 40 performance points, because 45 is going to be the base score. You can see that even Dr. Bach's implementation got 45 points. So whatever you get from 45 to 90 will be mapped to 40 points, and that will be your 40 performance score points. In terms of getting started a little more, Dr. Bach's lectures, memory lectures, talk about his implementation a little bit more, as well as how to actually implement Malloc and Realloc and use those in your functions. Yeah, he talks about that a little bit more. That's really it. This project isn't too bad. It's just a lot of debugging stuff, I think, like the previous project as well. But yeah, any questions? Or if I should go over something again, if it wasn't clear. I did go through that a little fast. Well, I wanted to read, Benjamin asked how soon will the video and slides be posted. I'm just gonna redraw the thing, so probably later tonight or early tomorrow morning. The 12 mod 16 part. Yeah, sure. I can go into alignment again. Don't really have anything here, but so when you first allocate something, you have a header, a payload, and a footer. So what you're going to be returning to the user is going to be this address here, because this is the payload here, right? So you're going to be returning the address here. So the address has to be 0 mod 16. So it has to be a multiple of 16. So what that means is, because we have a header here, and we know that the header is 4 bytes, because if you look at the code, it says int1 and int31, sorry, which makes 32 bits, which is 4 bytes. So if this is 4 bytes and we need the payload to be at 0 mod 16, then this is automatically going to be 12 mod 16, right? Just by the basis of the math. So then when we have a footer and we have the next payload that comes here, and then another payload here, which is whatever, we still have to make sure that this payload is at 0 mod 16, because every single payload address that's returned needs to be 0 mod 16. That's a requirement of the project. And then again, we know because the header is 4 bytes here, this needs to be not 8. Needs to be 12 mod 16. And so the footer and the header are going to be the same boundary tag object, just put in different positions. So then this footer is also 4 bytes. So then this becomes 8 mod 16. So it's a lot of pointer arithmetic more than anything else. You just have to figure out how to pad it enough so that everything aligns, essentially. Does that make more sense? Cool. word and W size. So Mark's just asked, what is word and W size in Dr. Bach's implementation, and is it the same? Is the word size same as the header size? Let me just show that. So what that actually is W size is just a macro that Dr. Bach has defined somewhere. Yeah, see, W size is just the size of the boundary tag object. So in that way, you can simply just say this pointer plus W size is going to give me the payload if you start at the header's address. And then when you say word, are you talking about the parameter word? Or, okay, yeah. I mean, again, that's just a, so if you look at extend heap, it takes in a parameter called words, which is just the size. But when it's passed in here, you see that it's given extend words, which is the max of a words or chunk size. So chunk size here is just the minimum size that Dr. Bach has set for a block in his allocator. That can vary depending on what your implementation is. A words you'll see here is, so he aligns the size divided by W size, which is the, like I said, the size of a boundary tag object as he's declared earlier. So here, Dr. Bach is dealing in words, which is going to be 4 bytes based on his boundary tag object, but that's his struct. So when you're actually implementing it, it's going to be different. You can deal in just bytes if you wanted to, really. That, again, that's more of a coding thing rather than an implementation thing. Well, no, so you can't necessarily define a word to be a different size. What the word here is the boundary tag struct. So it has to match the size of whatever your struct is, if that makes sense. You see that min block size words is saying the minimum size block size in words is 4. And we see that up here. Dr. Bach says minimum block size is 16 bytes. Yeah, in this situation, yes. Yeah. Oh, I was replying to a Benjamin's question. It just happens to be the boundary struct is also the size of a word. Yeah. You have access to, well, the file is actually called mmgblack implicit.c. It should be in the repo on GitLab. So like that's what I was saying earlier. You should try to use some of the helper functions, and you can honestly use the struct. You would probably need to modify it a little bit so that you can have a free block as well that includes a list element, but overall it's a very good starting place. Zachary asked, list LM will be part of the payload sort of if we use the list.c file. So no, The list LM, so you're not having a list of blocks that are allocated. You're only having a list of the free blocks. So in a sense, yeah. So when you have a free block, the list LM will be kind of taking up space. That should be the payload. But when you have an allocated block, that shouldn't have a list LM anywhere in its struct. So you would kind of need two different things there. Is there, oh, okay, I guess I'll go back to the code. Marx asked, is there a particular reason what was it? Is there a particular reason the boundary tag is 31 bits? So if we see here, the boundary tag has 1 bit that's allocated to this in use, and then 31 that's allocated to the size int. And all that really means is we only need 1 bit for the in use because that's only going to be 0 or 1. And the size can be bigger to fill up the rest of the space. The reason it's 31 is so that it makes up an even 4 bytes, essentially. Yeah, exactly. Okay, Ben asked, are we actually storing the block struct somewhere? Yeah, essentially you're getting memory from the heap and you're casting it into that space in the heap. So you're getting a memory address and then you're casting it to that block struct or the boundary block struct, yeah. So technically it is going to be stored inside of the heap. You're just not going to ever return the address of the block struct itself to the user. You're just going to find the address from the payload and return it to the user. So it will be stored. Because if you weren't storing it, you wouldn't know the addresses of it. Does that make sense? Okay. Essentially, like, there's probably an example in the code somewhere, but that's the initialization. Let's look at extend heap. So if you look here, you're actually getting a certain address, which is BP, which is just the address of the extended heap. And then you're storing that into a block struct. So you're casting that space in the heap into a block struct. So then it has a header and a payload inside of it. So then when you're kind of returning it back to the user, you can just go to that block struct and return the payload. So it's all kind of a contiguous part of the heap with headers and footers. Because it doesn't need to. Sorry, Ben asked again, why does blockstruct not hold the footer? And also, the footer is more of like an endpoint flag, just so that things don't overlap. You don't really necessarily need a reference to the footer, just because you're using the headers to go through the blocks itself. So if you do header plus 4 plus payload, you get to the footer, and then you move past the footer, and then you get into the next block, essentially. They're used more as fences than anything, and since you're not going to be iterating backwards through the free list necessarily, or even the heap, you're going to be going forwards. The footer just serves as a block, and you don't need it to go through all the objects. Difference between a 64-bit allocator versus a 32-bit allocator. So that just means you're capable of referencing more locations in memory. So it's just going to be attempting, it means the trace files are going to be attempting to allocate more space. So that could affect performance depending on what your implementation is like. Yeah, I mean, again, you don't need to use Ben asked, so we essentially have to allocate it separately than the block struct. If you're using a footer, then yes, but I am talking about Dr. Bach's implementation here, and you don't have to pull everything from his implementation into yours. And another reason the footers are used are for coalescing, so that like if you have two blocks next to each other, then you can use the footer to check if the previous block is free instead of trying to go all the way back to that before the payload and all the way back to the header of the previous block. Any more questions? Okay. Sounds good then. I'll stay on a bit longer just in case anybody has any other questions, but you're all free to go. Yeah, no problem.